Okay, I think we can start. Thank you very much for being here. Today we have the pleasure of having Karla for a seminar. She will join SFGs in mid to end of March. And she studied her PhD in Inaue. From there, she moved to the Canary Islands for a couple of years. And then she did postdoctoral studies in Austin and now in Edinburgh. And today she's going to talk about the chemical history of galaxies. So, all yours.
Yeah, well, thank you very much. I'm Karla. I have been very good times in Teruel, really very nice, and I know very nice people. So I will speak about two different surveys. One is in the local universe, that is classy, and then I will go to the high-redshift galaxies with excels, and I will show the connections that are between two different chemical evolution patterns about that. So I'm working in the research group of Fargo Scotland. Here are some of my collaborators. So Fargo also classy, and we have joined these two excels and classy people. Okay. So as you see here, this is a picture, illustrative picture about different scales, different objects in our local universe, so a little bit redshift. But all these galaxies, all these star-forming regions have something in common, and this is the emission spectra. So the emission spectra, all these objects give us information about the chemical abundances of the ionized gas. There are physical properties like electron temperature, density, the chemical abundances of different elements, but overall the metallicity. That is a key property of these galaxies, and also is strongly related with physical properties of the galaxies, like the stellar mass, for example, that you can see here in this plot. So the shape of this stellar mass or this scaling relationship tells us a lot about galaxy formation and evolution. And the shape is basically doing by this building of star formation. Then we have outflows that remove this gas, and inflows of pristine gas dilute the metallicity. So this is really very powerful empirical relationship. However, we have another relationship that you will see in all this thing overall this talk. This is the relationships that tell us about the chemical evolution of galaxies. We have here this always as a relation with metallicity. I will show you later, but I will speak about in this talk about these elements in the first part, and then I will focus on nitrogen that has a unique nucleosynthesis. So for the first part, well, show you first the periodic table. You can see here how these elements are produced, basically with all these different stars, so these different scenarios. I will focus on Corcollite supernovae. I will mention something about asymptotic giant branch stars, and also Taiwan super. So I will focus in these elements. Okay, so I will go for my first part for neon, sulfur, chlorine, and argon. I will mention just a little bit of chlorine. And then I will focus on these elements, that is here. So carbon, nitrogen, oxygen. Oxygen are powerful elements to understand star formation history of galaxies. So you can see here in the color code how this produces elements. I will tell you later about this in more detail. So, but we can see now in a spectrum of these objects. This is where our galactic S2 region, the Orion nebulae, and you see all these very nice emission line. Of course, this is a high resolution spectrum for one small part of Orion. And you see all these emission lines. There are critical lines that we need to calculate the density and the temperature of the gas. For example, here I show 14363. That is a line that you will see commonly also on my talk. We have other lines, so for 3, we have nitrogen 2 that are really very important for that. And you also see that this is very weak lines. So here, in comparison with, for example, other lines like H beta We have here oxygens that we can have. And we also determine densities using sulfur lines, chlorine lines. So all this information that we can see here help us constrain the physical condition of the gas by using all these diagnostics that I showed here. There are other surveys, of course, and I had some reference there. So this is a very illustrative way of form of the X2 region. We have the cluster where we have these mass stars or V stars, and then we have a distribution of different ionic abundances of the different atoms. So high ionization ions are concentrated mostly in the center, and then you have in the around the edge of the nebulae, we have the low ionization ions. So in gas abundances, we characterize the metallicity using the oxygen because it's the most abundant, and also because most of the ions are observed in the optical. So we want to derive the ionic abundances. We have oxygen plus and oxygen plus in different ionization degrees, and we add these ions and we can have the total abundances of this element. Of course, we need the physical conditions, the temperature. We have a structure and temperature that are characterized for different ionization zones. And we want to derive this as robust metallicities. We need to characterize the ions corresponding to the different density. This is the more called direct method to determine so far the accurate robust method. But this is only for oxygen. The other elements, carbon, nitrogen, and these elements are not too simple. We need ionization correction factors. This means that we cannot observe all these ionization species in the optical. So one way to go is to have observation of multiple wavelengths, like in the UV or the infrared, like the MIDI, and we can complete these ionization states. But in case that we don't have this information, we need ionization correction factors. This is another way, another thing to do it, but I will not be able to tell. But this is a really very important to determine these abundances, total abundances. Then, now in the high-redshift universe, mostly, there are more like clumps of dense gas traced for other diagnostics, like argon 4 or an optical, carbon, that we need to consider more in detail the impact of the density structure in how we determine abundances. In the local universe, usually the impact is not too significant, it's there, but it's not visible like in the high-redshift universe. Again, I will not go in detail on that, but I don't just only to say that is also something there with the density. But now saying that, we have this methodology, and we can calculate for all these different objects that have also different scale, different redshifts, local, basically all is local, or ion. Then we have X real N101, and you see 5471 that I hope that work with people here in sector with this region. And then we have this kind of dwarf galaxies. This is 168, that is a very close analog, very low metallicity. So we can do that. But also my talk is referred to the high redshift. So all these lines that I show you from these star forming regions, we can see also high redshift. This is one of the spectrums, the first spectrum, the K with the HWST. And as you see here, we have all these emission lines, oxygen, hydrogen, and we can derive abundances. But the more surprising is that show the power of the HWST, what is line here. This is a galaxy of redshift 8.4, number 4 years the age. And this is very surprising because previously to James HWST, there were people trying to determine chemical abundances at redshift 1, 2, and sometimes they were not this line. They were using other calibrators. But to have this information, now we can trace the chemical evolution of the redshifts of these redshifts to redshift 0. I show you here again spectrums to high redshift 7 to 8.2 4. This is the previous spectra, and you see here the 4350 line. We can calculate metallicities. We can calculate neon abundances with this line. We can determine dust, the dust composition of these galaxies. Many of the things that we can do with the local universe, before we can do that now with JWST and this spectrum. But there are more. JWST is providing all these proposals, all this information. Here is one of the galaxies, JC11, that is very famous now in the community, overall in the chemical abundance community. You see now this spectrum, this is in the UV, all these emission lines for carbon, nitrogen, and very high ionization line. We have here all the optical lines that I showed before, and then we have the galaxies, right? This is also a diagram that shows the bright and then the redshift. So this is 3 galaxies that show here in this plot, and you see how it's a different, also maybe different population stars, the galaxies, but you see these very prominent UV lines, okay? We have now also MON, redshift 1444, I think this is the far galaxies, so far I think, remember? But this is here also these very nice optical emission lines. And we have nitrogen, carbon 4, and carbon 3, oxygen 3, that we can derive some properties. At this redshift, yeah, we use the optical. So we can determine metallicities, but we can do other things or try to approximate the value of metallicities in this region. So I will also show this spectrum, 6014, that is from one proposal from the group of Edinburgh, that they do photometry, they have photometry, and they try to prove that we have also very high redshift galaxy, redshift 14 something, but results are no, we have redshift 1354. For them was very like, oh, where is no very, very high redshift, but still, right, we can do something, we confirm the redshift now, and the surprise for everyone is like we don't have these very nice emission lines, but they can do other things with this observation. I will speak a little bit more about that, but I will not do something more specific with high redshift. Just only to tell you that observing also the local, we can add this physics to the high redshift. Okay, so and to understand these high redshift galaxies, we need also local star forming galaxies that have also this very amazing feature. And this is CLASSY. So CLASSY was created to try to understand these properties from the galaxies, but also the chemical composition using a combination of synergy, the UV and the optical. So CLASSY is 44 star forming galaxies and basically optical. Bias are related to high specific star formation. We have this nice galaxies here, different aperture from the Hubble, because. But one of the things that CLASSY is that cover different parameters, galaxy properties, like the ionization parameter, in terms of the ionization state of the gas, and also electron density. We have, again, the mass metallicity relationship, we have metallicity, stellar masses. So with CLASSY, we can try to understand these properties and see how this works also in high redshift by doing comparisons. So here again, some spectra for CLASSY. We have optical, and you see again this very nice spectra. This is from LBT telescope for 5 galaxies, and you see again this very high ionization lines. All the lines that we need to derive the physical conditions and properties for the galaxies. And of course, we have the UV. For the UV lines here, so you see these lines, carbon that we see in the high redshift. Again, we here see more detail, silicon lines, oxygens, the helium, also very high ionization that we also see in the very high redshift universe. But also we have other lines that also you can derive different conditions of the gas, like the neutral abundances with this, and other properties, studies with Lyman alpha and everything. I have here only very old list of the papers, but classes is still working in different topics. So the data for class is free. So we have in the different files the optical and the UV. If you are interested to explore more this spectra. So Ricardo worked here, I will be here. If you want to also speak about class, if you want to explore a little bit more this spectra, I think we'll be happy to do that. So yeah. Okay, so giving that for classy, I will start with these diagrams. Okay, so in this part of the talk, I will speak about neon, sulfur, argon, and chlorine. Okay, so how these elements form? Who produce these elements? It's basically massive stars. Here, follow this trajectory here. So you see this explosion of corpulate supernovae enriches the interstellar medium with these elements. So when we compare these elements with oxygen, as oxygen is also produced for massive stars, we can have this kind of constant line. It means that they had a similar or the same nucleosynthesis, basically. So I calculate for classy all these elements with the methodology that I did before and compare this plot. So this X here will change for neon, sulfur, or the element that I compared that provide only for massive stars. Okay. So this is the first plot that we show. Neon. And you see here the metallicity we calculate. So this is what we expected to have for the nucleosynthesis. And then we have dispersion that basically is fine, this dispersion. We compare with our solar abundances for neon, and basically we are there. This means that this is really very agreement what we are seeing here in the local universe, basically. We have this increase in neon that is a little bit weird because we don't expect that. We have so few galaxies, but speaking with Chaki Kobayashi, she told us that neon, a solar metallicity, have another isotope, other that is included in all this combination with nucleosynthesis, giving this increase in the neon abundances. In the beginning, I thought there was errors or something, but I think also the DESI is now having results with very increase in the neon abundances. This is about neon, that basically massive stars. Then we have the sulfur and argon. And sulfur and argon are a little bit more complicated. But what we found is like, this is a solar thing, and we have solar values of sulfur for classic galaxies. And we still don't know what will happen. We think that could be the ICF or a contribution, a different enrichment scenario. This is still not clear. There are other previous works that show that maybe it could be another, I don't know, source like Taiwan supernovae, but this is still not clear. And the case of argon is more different also, but you see here for low metallicity, we have this spectrum and we have this constant trend here, but then we have this steepen that maybe could be also the ICF, or we need another contribution for the different scenario. So this is still unclear, but the thing is like the ICFs could be play a role there. But there are other studies with a more larger sample of galaxies. This is from Esteban from the Canary Group Islands, the Instituto de Física Canarias. And you see here, this is now instead metallicity, we have the argon abundance, it's basically the total argon abundance. And you see a little bit with the chemical evolution models that there is an increase on argon overall, and this also attribute that to Taiwan supernovae. However, I think that is the opposite. But we still need to know what really happened and why we have this deficit of argon at higher metallicity. So now that we have this comparison with classic, what we want is to compare with high-redshift universe, right? So I will show first argon, that we are now with argon. Speaking about argon, so this is argon overall. We have metallicity. Classic galaxies are these diamonds. We have other extra regions here, and all these color points are different words from Thomas Staton for galaxies around redshift 2-3. They have Cecilia with Rogers, a galaxy of 3, redshift 3, and then, well, other galaxies. And basically, what we see with argon is these solar values here, also the high redshift. And at the beginning, I thought, well, maybe it's the ISF or something that we are not calculating, but now it's like a more constant this value that has solar here. And people, again, attribute to Taiwan supernovae. Chemical evolution models also from Chaki Kobayashi showed us that this is a model for the Milky Way, that basically we are having similar nucleosynthesis that is massive stars. Okay, so here argon again, now with Cecilia. These observations were after the classic papers, so I couldn't compare these observations, but you see here, again, these subsolar abundances with argon overall. They show here again with Rogers 2025. Also in the moment that I did classy for these alpha elements, sulfur abundances were not existing in this moment. So now with the sample of Cecilia with Roger, you can see again, this is classy, these subsolar abundances. And then we have the other galaxies and redshift 2-3 for this sample of Cecilia. So we can see how a little bit these subsolar values even more than the sample of classy. So this means again that possibly also sulfur and argon are produced for another star, well, other mechanisms like Taiwan supernovae, but it's still not clear given all the uncertainties that we have with the ICX. So here in the SFG, we will work with some galaxies with MIDI, try to understand the ACS better, and try to complete or try to more or less low metallicity to try to see improve this determination for these elements. I think this is key before to have some other scenarios in play. Okay, so well, this is the part of sulfur and argon, and finally with neon, that you see neon massive stars basically. So very well constrained. There is dispersion, but very well constrained. Local universe, high redshift. We don't have any of like any bias in something other enrichment. This is one of the first measurements of this galaxy that I showed before, the 8.4. And basically, the errors and the uncertainties are very consistent with the local universe. So neon is very well to and some takeaway to this first part of the talk. Well, in general, we don't have any apparent redshift evolution for these elements from redshift, this is tracing redshift lower than 6 to 0. Of course, there are still incompletes with argon and sulfur that we will check here in SFG. And yeah, so the other thing is trying to understand what is happening with this dispersion. But this is like the main takeaway for the chemical evolution of these elements for redshift 0 to 6. So now I will pass to a more little bit unique element. I think it's really very nice, this element, and there is a lot of attention now for nitrogen. You will see in some slide why. But just a nice reminder, nitrogen is produced for two different types of stars. First is intermediate massive star and massive stars. So we saw here how is the trajectory of the supernovae, and then after 1 year later, we have the HGV stars that are the main producers of nitrogen. Okay, so these different scales are very important but give us information. One is the first course of star formation, but we need a benchmark to try to trace this kind of star formation time scale, and this is oxygen, because oxygen is producing only for massive stars. You don't have any other thing there. So given that, we have these stellar time scales, but nitrogen has another thing. And nitrogen can be primary or secondary element. What it means that? First, carbon is producing for the cyclo CNO. Okay, so carbon need to be producing for nitrogen, and carbon is our seed, in this case for nitrogen. But if carbon is produced for helium and helium, this means that the element in this case will be primary. However, if the persistent seed of carbon is already there, you can have a secondary component for nitrogen. That is these two different nucleosynthesis. All these together here is in this figure. All these processes here in this figure, and it's a powerful diagnostic to understand star formation histories in galaxies. Just for all these mechanisms that have nitrogen. Carbon is in the similar way, knowing all these lower stellar masses that produce carbon. I will not speak too much about carbon, but we can think that it's a little bit similar to this. So we have all these processes here. A low metallicity, when we can generate carbon, we have, or nitrogen, we have this flattening here, low metallicity, and then we have here the contribution for AGB star, a higher metallicity. Okay. So, however, part of this dispersion that we have here is real for these processes, but something else is there for all these high dispersion for these guys. So it can be different mechanisms that can enhance this nitrogen. One of them are hydrogen star, shocks, AGN contribution, feedback. All these mechanisms have been studied for many years ago, trying to understand this nitrogen. These galaxies here are high-redshift galaxies. And you can see that there is a very high nitrogen overall that cannot be explained only for massive stars. And this is what is finding now in the high redshift, and the people try to do different explanations. I will not go in this explanation here. I will show this comparison with the local universe, with Galaxies and so on, galaxies at redshift 2.6, but I will just compare that objects. Okay, so, but just only to say something about the high redshift galaxies, one of the things that the people is more or less in agreement is some of these galaxies have very nitrogen lines, nitrogen 4, nitrogen 3, that are very weird in the local universe. You can trace different diagnoses that give you the high density gas for these galaxies. You can derive direct chemical abundances, show elevated nitrogen overall, R34, but carbon seems to be very local. And other thing is that there are compared sources. Here, this is a diagram also for Colin Donnan. And he showed here this galaxy that they were expected to have higher redshift, but they showed completely no emission lines. And they showed this plot saying that strong nitrogen 4 lines are more compact galaxies, and we are more in the more extended objects. This is what still they need to do more analysis, maybe add more source, or more data, but it seems this trend is in that way. But I will focus in the second part of my talk in two different cosmic epochs. One is at redshift 5, and the reason is because we have carbon and nitrogen simultaneously in the same spectrum, and this is really very nice. And then we can derive different chemical abundances, metallicities, and other elements, and then compare these observations with chemical evolution models to understand carbon and nitrogen. And finally, I will connect with the classic, with the local universe, to try to understand the dispersion that we see in this relationship. So our goals for the second part is try to understand chemical evolution for carbon and nitrogen at redshift 5, the first year, the age of the universe, and then to understand what other source of enrichment can exist that push nitrogen overall higher. Okay. So for that, I will use Excess, that is a JWST program leading by Alan Carnan and Feroz Colin from the University of Edinburgh. They have galaxies, star forming galaxies, question galaxies, And I will focus more on star-forming galaxies. This is stellar mass. This is the redshift that have the sample, and I will focus here at redshift 5.25. So for that redshift, for this spectra, we have two galaxies. Two galaxies at redshift 5. Then we can have here this very nice spectrum. You see here the carbon-3 line. We have more or less a helium, but here carbon-3. We have our line oxygen-3 to calculate temperatures, and then we have nitrogen. So with this information, we can derive all these properties, but we can just go directly to carbon and nitrogen. First is to try to see what is the source of ionization for these targets. So here is a very well-known BPT diagram that shows us where is the source of ionization. Basically, in this region, you can have the star formation galaxy, star formation, all the ionization due to star formation. So these galaxies basically are here delimited by still considered that is star formation where is there. No contamination for AGN. So these galaxies are really very in the pool of other observations, including Classy, other objects, Aurora. There also are star forming galaxies. And then we have the star formation rate and stellar mass to see what is the galaxy properties of these objects. And you see here that basically are there in the pool of the other objects, meaning that there is any particular distinction about these objects. Everything fine. So now that we have carbon and nitrogen, we can do this plot. So as I told you before, carbon has similar nucleosynthesis with nitrogen. So we expected that we compare with metallicity, everything go in a similar way. And you can see here the X2 regions in the local universe are 8.5. Then you have here galaxies and redshift 0. And then we have here other objects, the Lambda continuum emitters. There are galaxies with very high ionization, the gas. And then this is a little bit high redshift than this. So, and this is the work from isotope 2023, and they showed that nitrogen, or this ratio, is enhancement. Nitrogen is pushing in these directions. So it means that there is a difference here in the scenarios that enrich these galaxies just at this redshift. So they don't conclude something more than maybe a massive star that these wings can enrich nitrogen over. So we with that for these galaxies, this is the same plot: carbon and nitrogen, metallicity, our local galaxies, the Lyman continuum emitters that are from isotope 2023, and our galaxies. And first, what we can say is the metallicity for these galaxies. At this redshift, this is a relative higher, maybe than was expected, in particular this one here. And then we see this like nitrogen enhancement in this direction that we have for these two galaxies. So, more in agreement with the direction that is the Lyman continuum emitters. We have also here the galaxies are reaching more than 6. There are all these galaxies. Another thing that we notice in this study is like these two galaxies are, again, higher metallicity than these other galaxies. These galaxies are completely different, determining the nitrogen overall. That also is another thing that we can see here, but we notice this enrichment even on that. So what we conclude from this plot is that in there is a nitrogen enrichment in these galaxies. Carbon overall is still consistent with the universe and produced for core collapse supernova. Okay, so different scenarios for these high-redshift galaxies: massive stars, very massive stars, supermassive stars, but variations in the INF and everything. So this is our scenarios here. But using our observation that we have for these galaxies, we want to know what is causing this enrichment. And we work in a collaboration with Chaki Kobayashi, and we can constrain these chemical evolution models with information that we have. So here, just for you can have a reference, we have the local star forming galaxies Glassy, and we have the Lyman continuum emitters in our galaxies. here. So what we did is like with Jackie, we use some of her prescriptions, and we trace different INFs and standard, top heavy, included more massive stars, and bottom heavy, including more like contribution the intermediate massive stars. So what we can see is that the models can reproduce observations by using a bottom heavy INF. This means that the enrichment for these galaxies is basically AGB stars, okay? We try to play with a different range on INF, but the thing is like these galaxies are relatively high metal galaxies, okay? So what it means this means that the nitrogen enrichment is primary, that the carbon that is produced there before to form nitrogen basically is from helium and nitrogen, but alpha processes. We have carriers here, as you see. We have errors, very big errors, basically because we need the ionization correction factors for both elements. We have just two galaxies. So here in SFGs, so I plan to increase this with some archival data for other surveys that we have with GTRST to try to constrain galaxies at redshift 5 or something like that with archival data. So yeah, so then if we want to try to compare with other galaxies lower redshift than these two galaxies, we have again this plot when we compare classic galaxies at redshift 2.6. Even if I move these objects, and if I just have these galaxies with the same symbol, you see that local universe and redshift 2.6 have the same dispersion, and you want to understand why. So what is happening with that? So in classic here is really important because classic has a lot of properties that have derived from other people. For example, we can determine electron density, we have stellar mass, star formation, and we have feedback, also the outflows, the information of the outflows of these, the velocity of the gas of these galaxies. So in the case of density, we have here the sulfur density and nitrogen overall. And what we found here is a correlation between density and nitrogen overall. So high nitrogen overall means high density. Galaxies are redshift 2.6 seems to be follow this relationship. This relationship was unexpected and could be biased, okay? So, and then we have other diagnostic here, argon 4, and we try to select some galaxies here that have argon 4, not all of them. In particular, these galaxies, none of them have completely argon 4 abundances. Here is the densities that they trace this gas, and we don't have this correlation between these with the sulfur 2. However, we have still high and overall and high density, basically. So we still need to increase this information. There was a paper from the J survey, also not finding any trend like this for sulfur 2, but we still need to do some investigation about it. The other two properties I want to mention is star formation and stellar mass. There were previous work working in this relation to try to compare nitrogen overall and these two properties. However, for those studies, how they derive these different chemical abundances were with strong light calibrators. I don't have nothing against strong light calibrators. I really like it. However, here we have direct abundance determination for a physical condition of the gas, density, and temperature. And what we see with classic first is a lot of dispersion. So actually we cannot really trace something that can tell us what is happening. We can see here a little bit of flattening in this nitrogen overall for some fixed stellar mass, and then an increase of nitrogen overall as stellar mass, which means that it's evolution of these high stellar galaxies, mass stellar galaxies. And we have also the high-redshift galaxies that are follow again this distribution and the galaxies. But we find very, very good relation with the star formation rate. Also, for a very low star formation rate, we increase to higher star formation rate. And also, it was also surprising these high-redshift galaxies and even the very, very high emission like galaxies. However, we need to take into account that for galaxies at redshift 0, we have an evolution there for massive stars, AGS star. It changed to the high redshift galaxies, like since like much with the local universe, we have still other maybe time scale differences there. Saying that, what we can conclude here is like there is no apparent redshift evolution, at least redshift lower than 6 for these different properties. Another physical property that we compared was the outflows. So most of the outflows that we have in literature are from the optical, from some lines. So in Classy, having the advantage of having this UV spectra, the Worosh in French for Classy in paper 2022, we calculate the oxide velocity of the outflow for the neutral gas in the silicon 2 lines and you know the absorption line. So we took this information for the oxide velocity, and then we compare that with the natural number. And one thing that we found is like the high velocity of the outflow means like correlated with natural number. We have few galaxies. Maybe we can increase the sample here to see that is extension of this relationship. But for lower value, we have also a lot of dispersion. I have here also one of the galaxies, Sunburn R, it's here, that seems to have this relationship. Also, the outflow is determined using UV lens. One thing here that I would say is I also compare with density here. And this means that the dispersion probably is an interplay with the star formation rate, electron density, and feedback. So finally, we determine from the output property the mass lowering factor that refers to the relative interest of the outflow. And there were previous work from Sinn Féin, and I think it's also for John Chisholm, that they compare the mass loading factor with the stellar mass, finding a correlation between high stellar mass, lower mass loading factor. And then for the dwarf galaxies here, high loading factor. This means that the outflow is more efficient. However, what we found here with natural number is that, yeah, in fact, we have these very massive galaxies here, but the mass loading factor very low. And we try to interpret this like gravitational expression of feedback. This means that these massive galaxies can retain these elements here. I really want to explore more these observations or this result, because this is with the neutral gas, outflow from the neutral gas. I think the next future work is to compare this with more detailed observations of the outflows for the optical spectra. It will be nice to compare this plot again, or even increase these observations. But overall, this is my last slide. This is for Excel. The takeaways here is basically that we still need try to improve this or increase these galaxies and electrify to understand the natural enrichment here, do more chemical evolution models for try to interpret these abundances, and we find really consistent carbon overall prediction that for collapse supernovae. So we are still working in this part. And for Classy, well, we have more information for Classy. We still want to do other things, but I think the main message here is the strong correlation we find with the outflows, and then that this interplay with the star formation, density, and the gas. So, and what we don't find any other apparent evolution. And for the alpha elements, also there is a lot of work to do. So yeah, thank you. Yeah.
Thank you very much, Carla, for the super nice talk. Questions? Javi?
Can you go back to the last? So very interesting, but I lost. I got lost. So why do you think, or not, that the nitrogen would be? I mean, the nitrogen would be less probably to be retained than oxygen.
We thought that, so it was very unexpected. So Ricardo helped a lot here. We start to understand because we expected that in dwarf galaxies you can have less potential wells and they can expel this, right? But what we think here happen is like there is this kind of fighting between the gravitation and the outflow there to try to retain these elements.
But why nitrogen would be less retained than oxygen? Maybe I'm not understanding the.
Okay. Yeah, so could be these related also with differential outflows, okay? From RISUTI 2025 that explain this could be, okay? That differential outflows is basically, I think, removing more of the alpha elements at that, but I don't know if it's competed with nitrogen. Could be, but yeah.
Yeah, well, in that sense, so there is a prediction from simulations relating the higher eta, higher mass loading factor towards lower mass galaxies. If your N over O has a secondary production for the most massive galaxies, then you will have N over O versus stellar mass. You will find a relation as you showed. Relation. So how this, so these two relations are connected somehow, no?
Yeah.
So.
Because if the outflow is removing the gas, the oxygen, we still feel the AGV, they can be produced because at the end these are very evolved galaxies.
Yes.
Massive. And we still have this contribution for still these stars.
What I mean is that I'm not very surprised that you have for the low mass galaxies, so the feedback is more is able to remove metals easier than for more massive objects. But then the other elements are retained, so I don't see the problem exactly here. Maybe I'm confused.
I think maybe we will expect it like these water galaxies, so now they have more way to have these outflow components.
Yes. For a galaxy of 10 to the 7 solar masses with strong outflows, you will expect to remove metals, right? But you don't see an increase of nitrogen relative to oxygen, so a differential wind or differential.
Yeah, the thing is that this is high nitrogen for the metallicity of the galaxy. So this is about the metal maybe.
But the lowest mass systems here are not enhanced in nitrogen, right?
No, here it will be here.
Yes.
Around, right? So this will be like this here.
So for the blue dots there, you don't see any differential outflow effect. So
no. For a reason, I think that maybe positive star could be that remove, because if I understand the differential outflow, remove alpha elements, right?
Yes.
And so you say now that I got with you, the AGV star is still there producing nitrogen,
Same.
but if the outflow is removing,
It's interesting.
Yeah. So, but I think the follow-up is to be with the optical. because we see that maybe it's tracing different gas.
Can you go to the previous one? 36, I think was it 36, maybe 35.
This one?
Yes. So here, what I'm not sure if I understand correct, but the chemical evolution or the
Yeah.
nucleosynthesis evolution of galaxies at different redshifts seem to be, there's no difference. The only difference is in density that is shown in the next plot.
Yeah, so some of here is like we have this for classic galaxies that are rated 0. So this means that you have also some evolution there for massive star, G star. While in the high-redshift galaxies, we still don't know. So, for example, these very, very high-redshift galaxies, probably these ones that are also aligned with it, probably this other sort of ionization, because we can explain this nitrogen overall. So even if this is in that direction, that everything is here, at least for the redshift 2.6, we're trying to say that would be similar to the local universe. But yeah, I think it's different evolution. For example, here, that is this ongoing star formation for these high-redshift galaxies, but the other one, we still the contribution of HGV star for. This is like a different evolution there in the gas.
Also, like another thing that I'm kind of, I don't know, not critic, but this could, it easily seems that you could also make a straight line for the orange dots to make the best fit line there.
What?
But the blue line there that you see, it's like flat, and then like and there's a uprise between 9 and 10 solar mass. So I guess like one thing is there something happening between in these galaxies between these ranges, but also I mean I was saying you could also easily draw a straight line there to see there's a variation in.
Well, I think the problem here is specifically with stellar mass is the dispersion. So we can just trace a line here.
Yeah.
Just imagine that you remove all the things we left all classy, you don't have a line there.
Yeah.
Yeah. So the thing is try to compare also with other galaxies that reach 0, for example, and also that classy is biased to this kind of prime, it should be prime, very specific star formation, that the other more, say, normal galaxies that are here in this. So I think this is the thing with that. Now with Bessie, one of our collaborators have millions of galaxies there, and you will see here just
I see.
something there. Yeah. But I think the point is like this individual galaxies with well-defined properties, we can see what it really happens. But yeah, I think you are right in the sense that density will be something, and you have to disentangle all the
One another like very basic question I had, it was I think one of the first plots that you show there's different abundance for the chemicals from different processes, and then but like half of the things are empty, so I don't know what those, maybe the first slide or second one where you show the elements and where they come from, the periodic table.
Yeah.
Okay, well, you say that first.
Yeah.
Okay.
Yeah, here. So like this is abundance relative to the sun.
Yeah, the sun is here, the dashed lines. So
Okay.
this is where the relation for this. I was saying that neon, okay, as solar abundances, that 8.69 have to also increase or something there. Even sulfur and argon you see here, solar abundances, how is just maybe one supernovae. So this is the means that. Yes, very nice.
That's all from my side. Thanks.
Can you go to the VPT diagram that you showed?
This one, the second one.
So if you have nitrogen enriched galaxies here, Should you use a different line for the deviation because you have nitrogen here in the numerator? So maybe you have more nitrogen-rich galaxies that are across the line and might not be AGNs.
Yeah. So here are using, I think, Kaufman and Cooley.
Yeah, I think this is Cooley and this is Kaufman.
Exactly. Yeah. Also, I don't know if this is related, but in one of the talks on Alicia the conference, I think there is a paper about that there is a limit for these alpha enhancement things that you cannot pass. Average galaxy doesn't go for part of the limit. I don't know if you are also doing that. I don't know if it's also.
But even if you have
alpha enhancement, you will expect to be on the maximal
something
demarcation.
I don't know what line that is.
But it's another line that moves that to the right, or the Cooley line
up and in that direction. So yes, so you go higher in excitation and a little bit towards higher, into. Yes, that's the effect of alpha enhancement, if I remember correctly. This is.
But if you just have a lot of more nitrogen,
yes,
you would move right there, right?
Yes. Indeed, if you add the SDSS, the whole SDSS there, you will see a gradient towards a higher.
That's what I mean. That if you cut galaxies, if you discard AGNs based on this, you might be removing very nitrogen-rich sources.
Sure. Yes.
If they exist.
If they exist, yes.
Perhaps the diagram with the oxygen one would be better.
We don't have oxygen one.
Oxygen one is more sensitive to shocks.
To shocks, Sulfur 2, we have the sulfur 2 upper limit.
Okay,
And they are less in the direction. But yeah, we haven't.
Then I have another question about the NO versus OH.
For
Where you show the models.
From checking?
No, sorry. Before, this one. Are these outliers also, or they can be explained by spectral scatter?
I think there are outliers. I think, unfortunately, we don't have the spectrum for that. Yeah, some of them also as a high metallicity. Sometimes oxygen 3 for electricity is not there, and so that we use other lines. So.
Is there an explanation for that, or because these are objects that have super high metallicity and very, very low overall?
Yeah, but I think what will happen there is, I don't know. I can say many things.
Just if there is some consensus, or
no, really no, because also when I trace models, it's hard to represent this time. So I really don't know what's happened there. But one thing that I can say is first starting for the ICF for this, that we don't have this quality of the spectrum for this in particular, because I expected the move more to the bulk of the observation. Here's the sun. Also, this is extra regions, but not really.
Okay.
I have a couple of questions. So the first one is, I would like to know your opinion about warfare pollution. And the second question is about, so we are comparing high redshift galaxies, young galaxies, relatively young galaxies, with more evolved systems in the So the spectra looks very similar. So this means at some point that what it weights more to the emission line spectra is the very reasons that we mentioned. But Orion is not the case. So if you do the same exercise with Orion, so in other words, Orion is not exactly a very good analog of these pristine galaxies, right?
Yeah.
So, and this goes in the direction that for instance, for elements that you have channels, formation channels involving type 1 and type 2 supernova, which is a time delay, you will get some differences, perhaps. So what do you think? It is perhaps one way to address this problem of the significant scatter in all these relations goes in the direction to compare, so to restrict the comparison, local high redshift, to galaxies with very specific, boxes in the parameter, in the whole parameter space. Specific star formation rate, things that may affect the emission line spectrum. And one of these things is not only the age of the younger star populations, but also the accretion rate. When you go to high redshift, you have higher accretion rates, so you have more hydrogen available going into the galaxies. So do you think, for instance, for nitrogen, a difference in accretion or related with the triggering of the massive star formation could explain somehow part of this scattering?
Yeah. So I will return a little bit to Orion. I think you are right. I think in Orion we always observe one part. There are now some kind of software with this SDSS Sloan 5 that is mapping all this very entire X2 region now, maybe for the first time. And what I know from Orion and for my work in galactic X2 regions, and then we have also high density environments. Okay, that has not been too much explored because usually, typically, we say 100 centimeters to the -3 for density. And really, Orion has a density of 5,000, 6,000, I think, in other diagnostics. So at the end, the physics of nebular physics will be here the same in your environment. For this reason, I think you still need to study this gas structure, right? This gas structure to see how density affects to the determination on N overall. So the work, for example, Zoraida Martinez and also Matt Hayes, I found that just using 10 to the 6, I would say here these objects have density to 10 to the 6 centimeters to the -3. When you use this density for calculate metallicity, this moves everything here. So we are underestimating the metallicity. And I think these sources like Orion allow us to test in physics what is happening, no? And the another thing that you say, yes, I also think that people say that this is just a force of star formation. There is a transitioning of this nitrogen enrichment because in the nucleosynthesis part, there is like a concentration of the production of nitrogen, and maybe it's just a transition in looking clusters. I think with Glassy and what you say is increasing rates and all these things, I think we go for more specific maybe objects, but still having thinking in the part of the physics that is there in these dense environments. So and the other thing was
the accretion. So the inflows of
the inflows of
relative pristine or meta 2 gas, because if you find that N over O, for instance, with the stellar mass follows the same trend as any normal galaxy, why do we have this nitrogen enrichment relative to oxygen? So if there is some feedback that is ejecting more nitrogen relative to oxygen, for instance, like Matteucci, etc., you will see the same effect when you compare with the total stellar mass, right?
Yeah, or that the galactic IEGN and AGN could be enrichment, right? Could be enrichment before for some sort of ionization, and then when the involved gas can return to the interstellar medium, can mix rapidly and increase that. But also, I want to say something extra that usually people don't say about this diagram. Chemical evolution models cannot reproduce this flattening. If we reproduce this flattening now, it's because they assume that the nitrogen is coming from the core, this nitrogen primary, is for very massive star rotators. So still we have things to do in the local universe, or they also reproduce that with failed supernovae. So for having this natural, you see these models for Cristina Chapini, Alvin Mercedes Morales, this is would be like a big here for nitrogen that we cannot reproduce still with chemical evolution, not just saying massive stuff, normal one. Yeah, but I think there is things to do with this galaxy, maybe restrict the parameter space to go directly to understand this.
I think we have with the JPass, for instance, follow-up good spectroscopy. We have opportunities to increase the significance or to go to these kind of studies.
Yeah.
Systematic. Thank you.
Any question or comment? No? Let's Karla again. You're dismissed.
Cuanto mejor datos peor se sabe los pros.
Sí, sí, sí.
Gracias. Tengo mucho error.
Sí, no te preocupes.